This is lesson 312 on similarity. We're going to look at more similar shapes today using the rubber bands, or if your teacher's using tracing paper, they're essentially the same thing. So we are looking at triangle ABC here, which I've already plotted. And we're going to use the method from yesterday to enlarge it by a factor of 2. Okay, so we are making it twice as big. Now, if you were using the rubber bands, remember you had the start of your rubber band, and then maybe you had the first loop. So then you're looking for where the second loop is to stretch it. Okay, if you were using tracing paper in your class, it's a similar idea. With the tracing paper, you're seeing how long this segment is, and then you're just bringing it over, sliding your tracing paper to make it twice as long. Okay, so that's where the second B is going to be. Again, same sort of idea as the two rubber bands. From A to C, if we want it twice as long, it's like we're going to extend that twice, so 2 of those, so the other C is going to be down here. So our new triangle in pink, triangle A prime, B prime, C prime, is this large. And so they want us to find how long each one is. Okay, AC down here in the green was 1, 2, 3 blocks long. And then AC prime, or A prime C prime, is 1, 2, 3, 4, 5, 6 long. Okay, BC right here is 1, 2, 3, 4 long. And then B prime C prime is 1, 2, 3, 4, 5, 6, 7, 8 long. And now AB, because this is a diagonal, we're going to need to use our Pythagorean theorem that we learned about in the previous unit. So for regular triangle ABC, this was 3 long, this was 4 long. So if we use 3 squared plus 4 squared equals C squared, right? 3 squared is 9, 4 squared is 16, and those add up to 25. So C is going to be the square root of 25, which is 5. So AB is 5. And then AB prime, when we do the same thing, this is now going to be 6, 8, and C. And that's going to get us 36 plus 64 equals C squared. Okay, and that's going to end up getting us 10 for A prime, B prime. Okay, now they want the perimeter of ABC, so we'll just add up 5, 4, and 3. So that's going to be 12. And then they want the perimeter of A prime, B prime, C prime. So that is going to be 24. Okay. So Monica dilated ABC to get a different triangle, and she knows that AB is 20 units long. How many times larger than triangle ABC is triangle A double prime, B double prime, C double prime? Okay. So it looks like when we dilated it by a factor of 2, this original triangle, each side got twice as big. Okay. So the triangle that Monica used, A double prime, B double prime, was 20 units long. The original AB was 5 units long. So basically, what did we dilate this by to get from 5 to 20? Okay, and you might know that 5 times 4 is 20. So this was dilated by a factor of 4. Okay, so essentially she used 4 rubber bands. So triangle A double prime, B double prime, C double prime is 4 times larger than the original triangle. And then therefore they want to learn, or they want to know how long B double prime, C double prime is. Okay, the original BC up here was 4. So we are making this 4 times as big. Then this is going to be 16 units long. So we have this idea of similarity. When two figures are related by a series of transformations, like a dilation, right, they are similar. So similar figures have the same shape, but not necessarily the same size. For instance, this cute little doggy over here, it's the same shaped doggy, but it's just much larger. Okay, so we would say these are similar, not the same, just similar. So similar figures can be created by multiplying each side by the same number, and that is called the zoom factor. Okay, so like for instance, when we were saying that this triangle is 4 times larger, we would say it has a zoom factor of 4. Okay, so this image has a zoom factor of, well, let's see, 5 times what would get us 15? How much larger did we make 5 to get to 15? The answer is 3. So this image has a zoom factor of 3. So we're going to enlarge this figure below by choosing one of the zoom factors. So the original shape has a side of 6, 6, 2, 2, 8, 4, 4, and 4. So if we want a zoom factor of 1, we are keeping all of these the same, right? If we multiply all these numbers by 1, it's going to have the same length for each side, okay? So this is a zoom factor of 1 right here. Next, we're going to go and chop everything in half. All right, here's the zoom factor of 1/2. We chopped every length in half, so this is now 3, 1, 2, 1, 3, and 4. Here's a zoom factor of 2 now. We multiplied every side by 2. So these are 12 long, these are 4 long, 8, 8, 8, and this is 16 long. And then here is our dilation by 3. Every side got 3 times bigger. So this is 24, 18, 6, 6. These are 12 long and 18. Okay, our shape got 3 times as big. So we're going to look at the different C's that we created in this problem. When the zoom factor was 1, it stayed the same. Right? When you multiply any number times 1, it doesn't matter what it is, it's going to stay the same. So 42 times 1 is still 42. Okay? So zoom factor of 1, nothing changes. If our two shapes are said to be congruent, here's a word you might have heard before. There is any series of rigid transformations that can carry one shape onto another. Okay, so no matter what we do to it, rotation, transformation, translation. So for instance, we're going to use our tracing paper to verify that these are congruent. So maybe if I traced over this and I moved it around, this is kind of what you do with your tracing paper here. If I just rotated this, can that fit? Yep. If I rotated this, yes. So really all I did was rotate these. They didn't get any bigger, they didn't get any smaller. So they are the exact same shape, size, so they are congruent, okay? Then we have something called ratios of similarity, okay? A ratio can sometimes be displayed as one number, a colon, and then another number. This is one way to do a ratio. Okay, or another way to do a ratio is with a fraction bar. Okay, these are the same thing. So with ratios of sides, the way they have set up these sides is that we have the side 8 over here and the side 24 over here. They put those in a ratio together because they are the same side of each shape, just on the different shapes, right? So that's that ratio. They did the big over the small. So then they did another ratio over here with the bottom sides of each C shape. Okay, again doing big over small. Okay, and setting up those sides in a ratio. So if we want to know if the ratios are equal, we can set them equal to each other and see. So on the left side of the C, that ratio sides was 24 over 8. Is that equal to 18 over 6? Well, let's simplify these. 24 divided by 8 is 3. I'm going to move this up a little bit. That is 3. And 18 divided by 6 is also 3. So because the ratio of the sides are the same, that means that this side, the purple sides, have been multiplied by 3, and the red sides have been multiplied by 3. Because each side was multiplied by the same amount, these triangles are, or I'm sorry, not triangles, these C shapes are similar, okay? Each side was multiplied by the same amount. We saw that because their ratio of sides were the same, okay? So we're going to do the same thing here. We're going to find another ratio of sides that are equal, okay? So this is the same shape here, but we could set up the ratio a different way. Okay, they did big over small. What we could also do is we could keep the ratio within the same shape. We could, instead of big over small, we could switch those around, and we could also do the ratio of sides where we had the small one on top and the big one on bottom. So we could start with the small side, 6, and the big side on bottom, 18. And then we could also do 8 and 24. And this becomes 1/3 and 1/3. So one way that we can use ratios is that we can find a missing side of a shape. Okay, so if we set up a ratio, let's do the left side in a ratio together. And let's do the big over small. I always like having the bigger one on top. It just means I don't deal with icky fractions. And then we can set this equal to the big side over the small side, okay? Because we're hoping that these are similar. Actually, it's the same shape. We know these are similar, and we're trying to find out what x is. Okay? In our algebra boot camp, we talked about how to cross multiply, so we can do that here. This is where we just multiply the diagonals of each fraction. So we would have 20 times 6, and then 8 times x on the other side. Okay, 20 times 6 is 120, and that's equal to 8x. So we can divide both sides by 8, so that x is 15. So that missing side is 15. And we can check to make sure that we're right. Okay, if we plug this back in, is 20 over 8 equal to 15 over 6? This simplifies down to 5 over 2. And this simplifies down to 5 over 2 as well. Those are the same. X is 15. All right, assume one triangle has sides length 6, 7, and 10 units. Okay, so let's make that triangle 6, 7, and 10. While another triangle has side lengths 3, 4, and 5. Okay. Are these triangles similar? Well, we learned that the way to test this is to make sure that the ratio of their sides are equal. So let's set up the left sides in a ratio first, 6 and 3. And we're hoping that this is equal to the ratio of a different set of sides. So let's do 10 and 5. Okay? So is that equal to 10 over 5? And we know these well. 6 over 3 is 2. 10 over 5 is 2. Because the ratio of their sides was equal, these are similar triangles. Yes. We're going to do something similar over here. They are telling us it's similar, so we are allowed to set the ratio of their sides equal to each other and solve for x and y. So let's do one involving x first. So let's do big over small, x over 11. We're going to set that equal to, we should do the side where we know both the numbers, because we don't want to do that where we have to have y and x in the same equation. So 24 over 8. And then we can cross multiply like we did before. 24 times 11 is 264, and that's equal to 8x. And then dividing both sides by 8 means x is 33. So this side is 33 over here. And then we can do the same thing for y. Okay, so big over small, 18 over y. Let's set it equal to the same set of sides in case I was wrong about what x is. And again, I'm going to cross multiply. So 18 times 8 is 144, and 24y. So if I divide 144 by 24, I get that y is 6. Okay. I'll let you fill out the key concepts on your own, but let's move over to some check your understandings. So these two shapes are similar and they want to find FG. Okay. So again, I'm going to set up a ratio of sides. So why don't we do small over big, just to remind you that we can do that. 3 over 9, we'll set that equal to the top sides. So 7 over x. I'm going to cross multiply. So 3x equals 63. So x equals 31. Okay. So they want to know the zoom factor. Okay. You know what? I did this wrong. I'm so sorry. This is 21. 21. So they want to know the zoom factor. So essentially, what did we do? What did we multiply by to get from 7 to 21 or from 3 to 9? We multiplied by 3 each time, right? We have a zoom factor of 3. Each side got 3 times bigger. All right, they told us these two triangles are similar, not drawn to scale. Super important, okay? Don't get freaked out when it looks like your picture's wrong. A lot of the time we don't draw to scale. But they want to find the length of DF, okay? So we can set up a ratio again. Let's do the left side, so let's do 16 over 4. And then let's do the bottom, 5 and x. You know what? X needs to go on top if I'm doing big over small. Okay, then I'm going to cross multiply so that 4x equals 16 times 5, which is 80, and then divide by 4 so that x is 20. And then they want to know our zoom factor too. So essentially, what did we multiply by to get from 5 to 20 to get from 4 to 16? The answer is 4. So we have a zoom factor of 4. All right, we have more similar shapes again. We're going to set up our ratio of sides. Let's do the 8 and 20 because they are the same side on the triangle. And let's solve for x first. So that's going to be the bigger side, x over 6. We're going to cross multiply. Oh, you know what? Did we already do this problem? No, we didn't already do this problem. Okay, so 20 times 6 is going to be 120. And that's equal to 8x. And so then we can divide by 8. So x is going to be 15. Okay, and then we can set up the other ratio with y. So let's do 20 and 8 again, but this time we'll do the 25 and y. Okay, cross multiply. So 25 times 8 is 200. That's equal to 20y. And 200 divided by 20 is 10, so y is 10. Okay, the zoom factor of the dilation, how did we get from 8 to 20? How did we get from 10 to 25, well, what we can do is just take one of our ratios, like 20 divided by 8, and that is 2.5. So this has a zoom factor of 2.5. Each side was multiplied by 2.5 to get to the bigger triangle. All right, then on to the spicy. We just have some more annoying numbers here, but same sort of deal. So these two sides, 4.5 divided by 1.5, and x over 2.2. We're going to cross multiply. So 4.5 times 2.2 is 9.9 equals 1.5x. And then, of course, we'll divide by 1.5. And we get 6.6. Okay? And then same thing with the y. We're going to use 4.5 over 1.5 again, but then we can set that equal to 9.6 over y. Cross multiply. 9.6 times 1.5 is 14.4, and that's equal to 4.5y. We can divide 14.4 divided by 4.5 to get that y is 3.2. Okay, and then to get our zoom factor, we can just take one of these ratios, like 4.5 divided by 1.5. to get 3. And then finally, we've got two triangles still. It doesn't maybe look like there's two triangles, but we have this small one, and then we have this big one. And the small one is just inside the big one, okay? So the big one has a side of 8 plus 4, so that's 12. The small one, this is 8, this is 6. So they want us to find DE, so that's the bottom on the big triangle. So we can do 12 divided by 8 is equal to x divided by 6. Cross multiply, so 72 is equal to 8x, and 72 divided by 8 is 9. So that side is 9. And then the zoom factor, again, we can just take one of our ratios of sides, like 12 divided by 8, and we get 1.5. So this triangle has been dilated with a zoom factor of 1.5. Every side has been multiplied by 1.5.